Hi, in the last video, we found out that the Nernst equation gives us the equilibrium potential for a single ion, that is the membrane voltage at which that ion has no net tendencies to move. For potassium, that is around minus 95 millivolts. For sodium, it is plus 60 millivolts, and for chloride, it is around minus 65 millivolts. But the actual resting membrane potential of a neuron is about minus 70 millivolts, not minus 95 or plus 60. It's somewhere in between, and it's much closer to potassium than to other ions. But why? Because the cell membrane is permeable to more than just one ion at the same time. And in this video, we will figure out exactly how and why these ions determine the resting membrane potential. Let's start with the key concept, the driving force. The driving force of an ion is the difference between the actual membrane potential and that ion's equilibrium potential, also known as the Nernst potential. Think of the driving force as the net voltage the cell is exerting on the ion. Just like in basic electricity, same charges repel and opposite charges attract. If the driving force is positive and the ion is positive, they will repel, so the ion is pushed out of the cell. But if the driving force is positive, but the ion is negative, they will attract, so the ion is pulled into the cell. Flip the sign and everything reverses. And every ion has its own driving force. So potassium has one, sodium has a different one, and chloride has yet another one. Each ion only cares about the voltage relative to its own equilibrium, not anyone else's. Let's put numbers to it. The membrane potential is minus 70 millivolts, and the potassium equilibrium is minus 95. So the driving force is around 25 millivolts. So the driving force is positive, and potassium is a positive ion, so they repel. So potassium is pushed out of the cell. For sodium, it's around negative 130 millivolts, so the driving force is negative and sodium is positive, meaning they attract. So sodium is pulled strongly into the cell. We can see that sodium's driving force is about 5 times larger than potassium, so sodium wants in much more urgently than potassium wants out. But the driving force alone does not tell us how much current there is. That depends on how easily the ion can actually cross the membrane. And how easily an ion crosses the membrane depends on how many channels are open for it. In electrical terms, this is called conductance, and it's the inverse of resistance. High conductance means low resistance, so current flows easily, and low conductance means high resistance, so current is blocked. For the cell, the conductance to a particular ion depends on how many channels are open for that ion at any given moment. In physiology, you will often hear the word permeability, and it's used to mean essentially the same thing as conductance. Whenever you hear that the permeability is high, translate that to more channels are open. Ohm's law states that the current equals conductance times voltage. For ion channels, the relevant voltage is not the absolute membrane potential. Rather, it is the driving force. So the current carried by an ion depends on the driving force. If the membrane potential equals the ion's equilibrium potential, the driving force is zero, and no net current flows, even if many ion channels are open. But if the membrane potential differs from the ion's equilibrium potential, then current flows. The amount of current is proportional to both the driving force and the conductance. At the resting potential, the cell is in a steady state, so no net charge is building up on either side. This means that the total current across the membrane is zero. This does not mean that no ions are moving. Potassium is still leaking out and sodium is still leaking in, but the movements balance each other out. So we can write that the total current is equal to the potassium current plus the sodium current plus the chloride current, and at equilibrium, the current is zero. We can also substitute Ohm's law for each ion, and that gives us the following equation. Expanding the brackets and collecting all of the membrane potential terms on one side gives us the following. Next, we divide both sides by the total conductance, and we get that the membrane potential is equal to the following equation. This is the chord-conductance equation. The resting membrane potential is a conductance weight average of all three equilibrium potentials. Looking at what the equation is saying, the membrane potential is pulled towards whatever equilibrium potential has the highest conductance. If potassium conductance is largest, as it is at rest, then the membrane potential sits close to the equilibrium potential of potassium. But if sodium conductance suddenly rises, as it does during an action potential, then the membrane potential swings towards the equilibrium potential of sodium. So, the resting membrane potential is not a fixed property. It is a tug-of-war between the ions, and conductance determines how hard each ion is pulling. So now that we know the equation, let's plug in real numbers. For a typical resting neuron, the equilibrium potential for potassium is around negative 95 millivolts. For sodium, it's around plus 60, and for chloride, it's around minus 65 millivolts. To calculate the membrane potential, we also need to know the relative conductances of each ion, which are shown here. Now let's plug the numbers in. And that gives us that the membrane potential is around minus 82 millivolts. That lands us somewhere between the equilibrium potential for potassium and chloride, far from sodium, because sodium conductance at rest is very tiny. So the membrane potential at rest is predominantly dominated by potassium. Another elegant way to see why conductances add in the denominator is to think of each population of channels as a resistor. When resistors are wired in parallel, their conductances will add up. So ion channels look exactly like this. Each is a separate parallel path for the current across the cell. So the total conductance of the cell is the sum of all those paths, which is exactly the denominator in our equation. So the equation we just derived, the chord-conductance equation, is a powerful tool used widely in physiology. But there is also a more rigorous version called the Goldman-Hodgkin-Katz equation. So this equation uses permeabilities instead of conductances, and the result has the ions inside the logarithm, similar in structure to the Nernst equation, but with multiple ions at once. In practice, both equations give similar predictions for the resting membrane potential. So to summarize, the resting membrane potential is not set by any single ion. It is a conductance weight average of each ion's equilibrium potential. At rest, potassium dominates because so many potassium leak channels are open. That is why the membrane potential sits near minus 70 millivolts, close to the equilibrium potential of potassium, but pulled slightly off by chloride and sodium. In the next video, we will see how sodium-potassium ATPase influences the membrane potential. We will also look at what happens when conductances change, specifically when voltage-gated sodium channels open. And that is where everything we have built so far will come together. So thanks for watching, and I'll see you in the next video.